Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 9, Lesson 1 on the area of rectangles. Now, Unit 9 is all about area. That's what we're going to be doing in this lesson, and in general we may also see a little bit of perimeter work. But generally speaking, what we're going to be looking at in this unit is sort of two-dimensional figures, common types of figures like rectangles, and how to measure the space that lies inside of them. So let's get right into that in the first exercise where we review a common way of finding the area of rectangles. Now, it's really important to understand that when we do geometric measurement, all right, we're always measuring some kind of property. An area is a measurement of the two-dimensional space that lies inside of a figure. It is often measured by counting how many squares of a certain size lie within the shape. That's why you might hear something like, well, the area of that is 5 cubic centimeters, or the area of that is 5 square feet. All right? So we're always kind of counting. We're just like, oh, well, there are 18 squares of this size that fit within that shape, so its area is 18 blank. All right? So let's start to take a look at that in exercise number 1. The rectangle shown below has a length of 8 centimeters and a width of 5 centimeters. A, using a straight edge, connect the points marked off on opposite sides of the rectangle with line segments. All right, so that's going to take you a little bit of time. Why don't you pause the video now? And again, all I'm saying is, take like that point and connect it to that point and connect it to that point, and then going across as well. Take a few minutes to do that. All right, well, for us, there's our grid. I didn't want you to suffer through me trying to draw those straight lines. Now again, I want you to really understand, right? These measurements, the 8 centimeters and the 5 centimeters, they are obviously measurements of length. I mean, granted, we called one length and one width, but whatever. They're measurements of distance. They are one-dimensional measurements. Okay? And literally, if you took out a ruler and your teacher didn't photocopy and shrink or enlarge these things at all, you would find that this is 5 centimeters in that direction and 8 centimeters in that direction. Now let's take a look at letter B. Each square that is inside of the rectangle has a shape and size shown below. What is this small square's area? Well, again, just to be very clear, if I took this square and I moved it up to there, right, it sits right inside of there. So in other words, this square has this side length of 1 centimeter and this side length, which is 1 centimeter. In fact, let me bring this guy back down here, right? Literally, this is 1 centimeter, this is 1 centimeter, this is 1 centimeter, and this is 1 centimeter. So this is what we call 1 square centimeter. Sometimes, many times, teachers will abbreviate that by putting down the normal unit like this, and then they'll write down an exponent of 2. Remember what exponents are, right? They're when we take something and we multiply it by itself. So, we think about this as squaring. Remember how we talked about, that in terms of an exponent. 1 square centimeter, sometimes people will say 1 centimeter squared. Really though, the correct way to think of it is 1 square centimeter, right? Oh, there's 1 square that has a centimeter on each of its side lengths. Now, letter C, what is the area of the overall rectangle and why? All right, so the answer to that, and then I'm going to have you think about it a little bit, is really how many of these squares would fit inside of this rectangle. So if you literally took the square and you were like, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. If you did that, how many of them would sit in there? Pause the video now and see if you can figure it out without actually counting them all out. Pause the video. All right, well, it's pretty much this easy, right? The area is 40 square centimeters. Make sure you're not saying 40 centimeters. That would be quite wrong. Or if you want to shorthand it, 4 centimeters, and then you put a little exponent there like that. Obviously, one way involves more writing than the other way. All right. Now, why is it 40 square centimeters? How can you think about that rather quickly, right? And again, I don't want any blind memorization of formulas or anything like that. I want you to really understand this. If I look at one of these rows, and I could look at a row or I could look at a column, but I'm going to look at one of the rows, right? How many squares fit in a given row? Well, there are 5 of them that fit in a given row, okay? And there are 5 of them that fit in a given row because this dimension is 5 centimeters long, or 5 centimeters in length. Then the question is, how many rows are there? Well, there are 1, 2, 3, 4, 5, 6, 7, 8 rows that have 5 square centimeters in them each. So, let me write this down. Each row contains 5 square centimeters, and there are 8 rows. So we just get 8 times 5, and that gives us 40 square centimeters. That's it, right? We're just counting the number of squares that are 1 centimeter by 1 centimeter, right? These size squares that fall into the overall rectangle. And we get that by taking this number times this number, because this number would represent how many squares would lie in a row, and this number would represent how many rows. Now, you could have also said, well, there are 8 squares that are in a column. A column is something that's vertical, a row is something that's horizontal. You could say, well, there's 8 squares that lie in a column, and then there are 5 columns, so I'd have 5 times 8, which is 40. But multiplication is commutative, so whether you look at it as 5 squares in a row times 8 rows, or 8 squares in a column times 5 columns, either way, you're coming up with 40 square centimeters that fit inside of this figure. And therefore, that's its area, right? That's just what it is. Now, over the years, you have certainly memorized the following formula, the rectangle area formula. The area A of a rectangle with a length of L and a width of W is just area equals width times length, or just put the 2 variables beside each other. Remember, when we have 2 variables touching each other, it means to multiply. Again, keep in mind, this formula is a direct consequence of what we just looked at. You can think of it as one of the numbers representing how many squares lie in a row and the other number representing how many rows, or vice versa. The amazing thing about this formula is that it works whether or not the side lengths are whole numbers, fractions, decimals. It doesn't matter. We still do length times width or width times length to find the area of a rectangle. Let's take a look at exercise number 2. A rectangle has a length of 7 3/4 inches and a width of 2 1/3 inches as shown in the diagram, which is not drawn to scale. Letter A. Why must the area lie between 14 and 24 square inches? Why is that? Where would these 2 numbers have come from? 14 and 24 square inches. Pause the video now and see if you can figure that out. Well, it's really quite cool, right? 2 1/3 lies between 2 and 3. 7 3/4 lies between 7 and 8, right? Let me just write that down. 2 3/4 lies between 2 and 3. 7, I'm sorry, that's 2 1/3, not 2 3/4. It's still the same thing though. 2 1/3 lies between 2 and 3. 7 3/4 lies between 7 and 8. So if I multiply the 2 smaller, 2 times 7 would be 14, And 3 times 8 would be 24, so the area has to lie in between that. And just think about it for a moment. What I'm really saying is, if I kind of went along this rectangle, right? If I went along this rectangle and I found where the 2-inch mark would be, which might be right about there, and then I found the 7-inch mark, which might be right about there, I would get that rectangle. That would be my 14 square inches inside of that rectangle. Then if I kind of extended this and went out to the 3-inch mark, and extended this and went out to the 8-inch mark, right? So if this was, let's say, 2 by 7, and this was 3 by 8, what it really says is that our rectangle would fit inside of the 3 by 8 rectangle, but the 2 by 7 rectangle would fit inside of this one. So somehow, our area must be between 14 square inches and 24 square inches. And that's important because our answer is going to be a little messy. And if it's not between 14 and 24, then we know we must have done something wrong. So let's take a look at letter B. Find the area of the rectangle in mixed number form. All right, so the area, regardless, right, is going to be 2 1/3 times 7 3/4. So let's just write that down to begin. Right, the area is going to be 2 1/3 times 7 3/4. All right. Now, that's somewhat challenging to do because these fractions are written in mixed number form. But we can convert them to improper fraction form, and then we can use our standard algorithm for multiplying two fractions to figure out the answer. So first, let's convert the 2 1/3. Actually, pause the video now and you do that for yourself. Convert the 2 1/3 and the 7 3/4 to improper fractions, right? Fractions where the numerator is larger than the denominator. Go ahead and do that. All right, well, 2 1/3 is the same as 7/3, and 7 3/4 is the same as 31/4. Yep, that's it. Now this is pretty ugly because there's no cross-canceling. 3 doesn't go into 31, 4 and 7 don't share any common factors, so there's no getting around this. I have to do 7 times 31, and I have to do 3 times 4. So maybe on the side of my paper, I do 7 times 31, and I get 217. And I don't think I have to do the 3 times 4 on the side of my paper. So let me just maybe move this guy out of the way. So my answer is 217/12, but that's not in mixed number form. That's in improper fraction form. Now I have to convert 217/12 back to mixed number form. Pause the video now and see if you can do that by using division. All right, well, let's go through it real quick just to make sure that we have that. Right, this is going to be 217 divided by 12. 12 goes into 21 one time. Do subtraction and I get 9, drop the 7. 12 goes into 97, I believe, 6 times. Let's take a look. No, not 6 times. How about 8 times? 8 times 2 is 16, carry the 1. 96, oh, that was close. Minus, and I get 1, right? So that means my answer is 18 with a remainder of 1, but then that becomes the numerator, and I get 18 1/12. Oh, shoot, I didn't use correct units. Let's get that. 18 1/12 square inches. Always want to have my units. 18 1/12. And again, it would be hard to know how realistic this answer is, but the great thing is 18 1/12 definitely lies between 14 and 24. It doesn't tell me that this is the right answer, but it tells me it's reasonable. If I had gotten an answer, let's say, of 32 1/4, that would be wrong because it would be too big. And if I had gotten an answer like, let's say, 11 1/2, that must be wrong because it would be too small. It would be below the 14. So it's good to be able to estimate areas, especially when the length and the width are quite messy. All right, let's keep going. Let's do a little more area work. The coordinate plane can be extremely helpful to model rectangles because it's a rectangular grid. And what we mean by rectangular grid, right, is because all of the vertical lines are perpendicular to all the horizontal lines, rectangles can easily be plotted in a coordinate grid, and then their areas can be found by using length times width or width times length. So let's take a look at that in exercise number 3. Rectangle ABCD has vertices, which are the corners of a figure, at A, 7, 8, B, 7, -2, C, -6, -2, and D, -6, 8. Answer the following questions. Letter A, plot the rectangle and label its vertices. All right, so what I'd like you to do is actually take some time, do that now. Make sure you remind yourself how to plot coordinate points that have both positives and negatives in them. All right, well, here we go. A is at 7, 8, so 7 here, 8 here. There's my A. B is at 7, -2. That's going to be down here. C is at -6, -2, right there. D is at -6, +8. I'm trying to get all these plotted in the right place. I really should use a ruler right now. I'm just going to plot it like that. Great, nice rectangle in the coordinate plane. Letter B. Label the length of each side of ABC on the generic rectangle shown below. All right, so in other words, it's great, it's obviously a rectangle, but I still need to know its length and its width to calculate its area and maybe its perimeter. So let's first get the length along the top. Obviously the length along the bottom are going to be the same. I can definitely see 5 units here, 5 units there, that's 10, plus another 2 is 12, plus another 1 is 13. So maybe 13 units across that way, and of course that would also mean I'd have 13 units down here. All right, the vertical, right, I can see that I've got these 5 units plus another 2 is 7, plus another 3 is 10, right? So I've got 3 plus 5 plus 2, right, gives me a total of 10 here and 10 here. All right, now granted, this rectangle has kind of a longer dimension here and a shorter one here, which isn't the case over here, but it doesn't really matter. We just want that picture so that we can very quickly then look at those dimensions and calculate the relevant things that they ask us for. In fact, right, letter C, state the perimeter and area of this rectangle, show the calculations you use to find both. All right, well, why don't you pause the video now and figure out the perimeter and the area. Don't worry about units given that we haven't specified any length units on here. There's no real reason to put any kind of length or area units down here. Just find their numerical values. Pause the video now and take a couple minutes. All right, well, recall that perimeter is literally the length that surrounds the figure. The length that surrounds the figure as opposed to the space that lies inside of the figure. So the perimeter of a rectangle, at least, is always equal to 2 times one of the dimensions plus 2 times the other dimension, because there's 2 of each, obviously. So we get 20 plus 26, and that gives us 46. 46 whatever. Inches, feet, miles, we don't know. The area is just length times width, and that's simple then because it's 10 times 13, or 130. All right, that's it. The coordinate plane is something that we'll use a lot for geometric figures, especially ones that have right angles in them, because it just lends itself so well to those kind of figures. Okay, let's take a look at one more problem. Here we go. Now, more complex shapes can be created by combining rectangles in a whole variety of different orientations. As long as we can break the shape down into its component rectangles, then we can calculate its area. Because obviously, if I slice and dice this thing up into 2 or more figures, and I'm just trying to measure the space that's inside of the overall figure, if I can figure out how much space is inside of each one of the individual rectangles, well, then I can add it all up to figure out the space inside of the total figure. Play around with this particular figure, either kind of like draw a line like that or draw a line like that. Draw lines in that divide it up into rectangles whose area you can find. Add those areas together to see if you can find the area of this overall figure. Play around with it a little bit. All right, the cool thing is that there's actually 2 very distinct ways of chopping this up. There's probably many more than 2, but there's 2 that are obvious to me, And the cool thing is, regardless of which way you go, of course you get the same area. Let's take a look at them. So one way to actually slice and dice this figure up would be to take this line segment and just draw it over like that, right? Now, what does that mean? It means we have a rectangle on the bottom that has a measurement of 5 feet by 9 feet. Let me call that maybe rectangle 1 and rectangle 2. So rectangle 1, right, is this rectangle that's just 5 feet by 9 feet. That's rectangle 1. And it would have an area of 45 square feet. On the other hand, rectangle 2, this one I have to do slightly more work on, because although I know this dimension is 6 feet, this dimension I have to actually do a little subtracting, and that's going to be 11 feet, right? It's going to be that 16 feet minus that 5 feet, that's 11 feet. Its area then is 6 times 11, or 66 square feet. And if I do 45 plus 66, I get 111 square feet as the area, right? That's it, 111 square feet as its area. That's pretty easy to remember. Let me put it right up here though, because it's really cool. The area inside of a figure shouldn't depend on the way you slice it up, right? If there are 111 squares that are 1 foot by 1 foot that fit inside of that, it shouldn't matter how I cut it up. There should be 111 squares that fit inside. So just for a moment, I'm going to erase all of this, and let's redo that by doing it in a slightly different manner. Let's see if I can erase all of this at once. Well, I can get most of it. Okay. Oh, it's all gone. Nice. All right, so remember, ultimately we're looking at 111. I want to get rid of all of this and finally this, because maybe some of you said, well, I see it this way. Maybe I cut it down that way, in which case let's call this rectangle 1 and this rectangle 2. That big rectangle, the very tall vertical one, right, which I drew really poorly here, would be 6 feet by 16 feet. All right, so that thing would have an area of 6 times 16, and that would be 96 square feet. And if you don't trust me, just do it on the side of your paper. Now, the smaller one though, rectangle 2, right? That one's got that 5 feet. We can see that very easily. But this dimension's a little bit trickier. It's got to be the 9 feet minus the 6 feet, and that's just going to be 3 feet. So that one's got a very easy area. 5 times 3, or 15 square feet. And now if I want the total area, I would do 96 plus 15, 1, and I get that 111 square feet. In other words, it doesn't matter, right? Regardless of how I chop that thing up, I get the same area of 111 square feet inside the figure. All right. I know that literally almost nothing that we did today was new, right? You've been finding the area of rectangles for a long time, primarily because it helps us think about multiplication, right? You know, thinking about how many squares sit inside of a rectangle are all about how many squares fit in a row and then how many rows fit inside of the rectangle. Therefore, right, we use one of the dimensions to count the number of squares per row, and we use the other dimension to count how many rows. We multiply them together, and we find out how many total squares fit inside of the figure. One of the most remarkable things is that that works even if the side lengths aren't whole numbers. You know, if they're fractions or decimals or whatever, we can still just simply take our length times our width and get an area. We also saw in this lesson briefly in the last exercise how you can take a figure that's actually constructed of multiple rectangles, slice it up into the individual rectangles, find the areas of all of them, and add together to find the space that is enclosed by the entire figure. Don't worry, we're going to get a lot more work on area as we go further in this unit, especially area of rectangles. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.